Hello everyone, in this video we are going to look at an end-to-end machine learning workflow for solving regression problems. Specifically, we are going to consider the main steps that we need to follow for developing a machine learning model for a regression problem. So we'll consider loading and inspecting the data required for the regression problem. Then we'll consider the pre-processing of the data as we have seen in the previous videos, and we'll train several candidate models like that of here, starting from linear regression to cut-boost regressor, and compare their performance using the R-square measure of performance. And of these candidate models, we may select one of the model as the best. Then next we have to identify the relative contribution of the input features, or we have to consider what you call feature importance or variable importance. So we'll consider this end-to-end procedures for developing an ML model for solving a regression problem. So today our focus is on a regression problem where the outcome variable of interest is that of continuous type or a quantity variable in general. So we'll consider linear regression, which is just the usual straight line model that minimizes the sum square of the error. Ridge regression, which is a linear regression that adds an L2 penalty for combating overfitting. And lasso regression, this adds an L1 penalty, and this L1 penalty performs some sort of feature selection. And elastic nets regression, this combines the effect of L1 and L2 penalties, so it makes a balance in between this lasso and ridge type of regression models. And there is also another type of regression model called Hooper regression. Now in the usual or in the standard regression models, the loss function minimizes the sum square of the errors, but this sum square of errors penalizes large errors more heavily, because due to the squaring process, squaring a large number will make it large. Therefore, this squared error penalizes large errors more heavily. So sometimes, in case there are some outliers, this sum square of error may not be that much appropriate. So we have also another type of loss function which is called absolute loss, which considers the absolute value of the difference of the actual value of the outcome variable and the predicted value of the outcome variable, and this absolute loss gives equal importance for each error. However, this absolute loss is not differentiable, so it is not usually utilized as a loss function for regression problems, but in the case when there are some outliers, it is just advised to use this absolute loss instead of the squared loss. So this Hooper regression is going to consider these two losses. If the error is too large, the Hooper regression will consider an absolute loss, and if the error is small, this Hooper regression will consider this sum square of error loss or the squared loss. So this Hooper regression is said to be a robust regression because it is less sensitive to outliers, or it uses the absolute loss for large errors or large residuals. And we have seen also that of the support vector classifier in the previous video. Today we are going to consider that of the support vector regressor that is applicable for regression problems. And we have also a k-nearest neighbors regression. Now this k-nearest neighbor regressor considers just the k-nearest data points. If we want to predict a certain value, let's say A, then it will consider the k-nearest neighbors to that point A. Then for this regression problem, the value of that point A will be considered as the average value of the neighbors. Therefore, if you consider k as 3, the 3 nearest values will be averaged, and the point A will be predicted as the average of those 3 values. And we have a decision tree regressor. This splits the data into different regions using certain decision rules, something like using if else, something like statement. So it doesn't have a certain regression formula like that of linear regression or linear support vector. It just splits. It is a tree-like structure. It constructs the data into the form that it looks a certain tree structure, and the decision will be based on certain rules. And there is also another ML algorithm, random forest regressor. This random forest regressor is nothing but it is a combination of several decision trees. Each decision tree will predict the value, and then for regression problem, the average predicted value will be considered as the final prediction of the model. And another we have also gradient boosting regressor. This is also a combination of decision trees, but unlike that of the random forest, where the decisions are parallel to each other and where the decision trees make prediction simultaneously, in the gradient boosting regressor, the trees are going to be constructed sequentially. Then each tree will correct for errors. Therefore here it uses, this gradient boosting regressor uses trees, but the trees are considered as sequentially. So the prediction is going to be performed in a sequential order, provided that they correct for the previous model's error. And there are also other related type of such ensemble methods like extra trees regressor, bagging regressor, ADA boost regressor, extreme gradient boosting regressor, and cut boosting regressor. So here for this, the common machine learning models starting from supportive vector number 6 up to number 15. In the case of having a classification problem, we need to just replace the regressor by a classifier. That is the only difference. We are going to use supportive vector classifier, k-nearest neighbors classifier, decision tree classifier, random forest classifier, and so on. Now let's load and inspect the data that we are going to use for illustrating this machine learning workflow. So the data that we are going to consider is the data that we have used in the first tutorial for illustrating a regression problem. So that's just the Boston housing dataset, and our outcome variable is the median price of the homes, and we have coverage like crime, proportion of residential land, and so on. So let's import these pandas and numpy libraries of Python. And now importing pandas and numpy is done. Now let's load the data that we are going to use. So this is our data that we are going to use for illustrating this machine learning workflow for developing a machine learning regression model. So price is our target variable or dependent variable to be modeled. If we are interested, we can look at the shape using the shape attribute of the data frame. So there are 506 observations and 14 variables, including that of the outcome variable. And we can call on the method describe to see the descriptive statistics associated with each numeric variable. So count, mean, standard deviation up to the maximum value is displays the values of this summary statistics. And it is also essential to examine whether there are missing values or not, and then if there are some missing values, it is essential to utilize missing value imputation techniques instead of dropping all the missing observations. So for that we need to call the method isNull, and over that we need to call the method sum to get the number of missing values associated with each variable. So here it is 0, that means every variable has no missing information. Now let's pre-process our data. Once we load or import the data required for modeling, the second most important step in machine learning modeling is preprocessing the data. That means we have to convert the data in the format that the machine learning algorithm requires. So the first thing that we need to do is we need to separate the input features data and the target features data. For now, just we have a single outcome variable, that's y. So we need to identify this target feature data and input features data. So prices are our outcome variable or dependent variable, so we have to exclude it to obtain that of the input features data. So housing if drop the price variable. So now the input features are separated in a certain data frame xdf. Now we have no price variable here, therefore this variable consists of the input features alone. And for the outcome variable, we have to extract only our price variable. So this is our outcome feature data or outcome variable data. Now we split or separate input features data and target feature data. So if you are interested, we can look at the information type using the .info method. So it says crime, zn, and so on, stats, floats, int. Now all the variables are here assumed to be numeric, but a numeric variable is not necessarily quantitative. For example, here, if you consider the variable that says chas, which is an indicator whether the house is near to the Charles River or not, it's a binary variable, but here it is treated as a numeric variable. So even if numeric, this variable is still qualitative. Similarly, if we have a variable having 3 or more categories, again, if those categories are numerically coded, the variable would be treated as numeric. And this numeric variable is not necessarily a quantitative variable. Therefore, we do not rely on the data types of these variables from this output. Rather, we have to identify our categorical and quantitative variables by inspection. Therefore, here, for example, I know that this Chas River or that of the Chas River indicator is a qualitative variable. Therefore, let me say our categorical features include only this variable. Only just we have one qualitative variable. And for those quantitative variables, all the others are quantitative, so I use these lines of codes. So here I have 12 quantitative variables, and here I have one qualitative variable. Therefore, here we need to identify once we separate the input features data and the output feature data, we have to identify quantitative and qualitative covariates from the input features data, because the transformations that we are going to apply on the quantitative and categorical are different. So now we have already identified categorical and quantitative covariates. So now we can split the data into train and test, and for that, as usual, we can use the train test split method. Then for that, we need just this train test splits. We need to supply the input features data, output features data, and the ratio let it be 20%. 80% will go for training data, 20% will go for testing data. Now the splitting is done. So we can look at the shape to see. Yeah, there are 404 observations in the training set and 13 variables. And what about for the test data? Yeah, in the test data, there are 102 observations and 13 variables. So we split the observations into train and test sets. Now once we split the data into train and test, next, most importantly, we have to transform our data. Specifically, the qualitative variables should be one-hot encoded, or we have to utilize dummy encoding, and the qualitative variables, the quantitative variables should be either standardized or should be normalized. So we can import this one-hot encoder from a scalar and preprocessing, and a standard scalar or minimax scalar again from the same module, and to apply the transformation for both categorical and quantitative variables together, we can import this column transformer from a scalar and compose. Then this will help us to transform both the categorical and quantitative variables together. So let's run this cell, and here the categorical transform, I'm going to use one-hot encoder. Let's drop the first category. That means the first category will be considered as a reference category for all those qualitative variables. And the quantitative transform, we can use this minimax scalar. In fact, for the chas variable, or here, it takes the value 0 and 1. We can pass it without just pre-processing because it is already coded as 0 and 1. But if we are interested, we can utilize this one-hot encoder, which makes no difference actually. So I can run this now. Categorical covariates. Why is it not working? Okay. Parameters, so one-hot, these are the specifications. The first category is going to be dropped, and the transformers are categorical encoder. Here's the ones we have defined here. Here, the quantitative scalar. Here's the ones that we have defined here. Therefore, here the categorical transforms using this one-hot encoder for those categorical input features, and the quantitative transform, this minimax scalar, normalizes those quantitative input features. So for the quantitative, just we are going to have a certain feature range because this is normalization. So that normalization is between 0 and 1. But if you are interested, we can change this one to, let's say, 0 and 2, 1 and 2, and so on. But normalizing the values in between 0 and 1 is the default feature range. Then now we have instantiated the transformer. The transformation is not done yet. It says not fitted. This is just an instantiation of our transformer. Then after instantiating the transformer, we have to fit the data. That means we have to supply the train data. And for that, we need to call the method fit transform over the transform model here. Fit transform, then we need to supply the training input features data. Then this will, one, fit the training data, and the other transform the training data. It performs two steps. Once I fit, it will extract the summaries required for normalization, and transform, it converts the data to the required format. So for example, here we can use dot fit like this, but this one only gets summary measures of the transformer. It doesn't actually transform the data. But when you use fit transform, it fits the data or gets summary measures of the transformation, and also transforms the data. So we need to call this fit transform for the train set. Now the data is transformed into all those qualitative variables are one-hot encoded using values 0 and 1, and all those quantitative variables are normalized into a value between 0 and 1. So the one-hot encoding is setting the values 0 and 1, and the normalization is setting a value between 0 and 1 inclusive. So just the one-hot encoding and the normalization are different. And the shape of this train data is 413. Just the same with that of the train set of the actual data set. And here we can get also here, for example, we have specified for categorical covariates. The transformed features will have a variable name including this categorical encoder, value of, name of the input feature, quantitative scalar, name of the input feature. So we can get those names using this get feature names out method over the transform. Then for example, the actual name of the variable chas in the transformed dataset is categorical encoder double dash dash chas 1. For the quantitative scalar dash dash crime, quantitative scalar dash dash zn, and so on. Therefore these are the actual names of the variables in the transformed sets. The actual names are crime, zn, this one, index, chas, nox, and so on. But when they pass through this transformer, they will include the names, these names, the ones that we have specified here, categorical encoder and quantitative scalar. And for those quantitative variables, here we are using normalizing, that means min-max scalar, so we can obtain the minimum value of the covariates and also the scale. The normalization is a little bit formatted in a different way. Just here let me consider this one. In normalization uses such kind of, for example, x, the standard deviation, is determined using this formula. So the scaled value is nothing but the standard deviation, this value, times max minus mean, then plus mean. So we can get the minimum value and this scaled value, or that's of the multiplicative factor used for scaling. So for the quantitative, I can just call this mean method over this quant scalar and this scale attributes over this quant scalar. And this quant scalar is actually nothing but it is obtained using that of named transformers for the quantitative scalar. So I can run this one. So for each of the quantitative variables, the first one is minus 0.0001, I think, and the other 0, and here minus 0.02, and so on. And these are the scaled, or the sort of the standard deviations, which are used as multiplicative factor for scaling. So in the test transformation, the transformer is going to use this minimum and this scale values to transform the data in the test sets. Therefore, for the test sets, we need to call just transform. Then this transform, we utilize these values for those quantitative variables. Therefore, for the train sets, we need to use fit transform. But once we perform this transformation on the train sets, the summaries or the quantities of the normalization or standardization from the train sets are going to be utilized for the test sets. So we just call this transform method and pass the training data. Therefore, these are transformed training sets, and if we are interested, we can look at the shape 102 and 13. And lastly, we can convert this the train and test target variable into numpy array. It's not a transformation, but here just I am changing the format into a numpy array. That means here the actual data, for example, here it is a pandas series, but when you convert as Y-train, it becomes a numpy array. Therefore, this is not a transformation, but changing the format or the data type of the output feature data or the target variable data. Now we have finished the soft transforming or pre-processing the data, or we have just converted the required data in the format that the machine learning algorithm requires. Now we can train several candidate models and we can compare their performance. So for linear regression, we can import, for example, for modeling linear regression from a scalar linear model, we need to import linear regression. For ridge regression, just from the same module, import ridge. For lasso. For elastic nets, and again for Hooper regressor. And for that of a support vector regressor, we have to import from scalar and SVM. Import SVR. If it is SVC, that is a support vector classifier. That is going to be used for a classification problem. But now we are focusing on a regression problem, therefore we need to call this SVR. And for k nearest neighbors, we can import it from scalar neighbors. Import k nearest regressor. And for classification problem, it could be k neighbors classifier. For regression, it is k neighbors regressor. And for decision tree regressor, we have to import from scalar tree because it's a tree-based model. Import decision tree regressor. For random forest, import from scalar ensemble because these are a combination of several decision trees. So we have to import random forest regressor. And for gradient boosting regressor, we have to import again from scalar ensemble. Import gradient boosting regressor. For extra trees regressor. For bagging regressor. And for ADA boost regressor. And for that of extreme gradients boosting regressor and cut boost regressor, first we have to install this XG boost and cut boost, and after that we can import this XGB regressor and cut boost regressor. So in general, here I wrote the code for importing all the models: linear regression, ridge, lasso, elastic nets, Hooper regressor from a scalar linear model, and SVR from a scalar SVM, and k-neighbors regressor from a scalar neighbors, decision tree regressor from a scalar tree, random forest regressor, gradient boosting regressor, extra trees regressor, bagging regressor, and ADA boost regressor from a scalar ensemble. But extreme gradient boosting and cut boosting or categorical boosting are not the part of that of the scikit-learn library. Therefore, we need to install them first using this pip install xgboost, pip install cut boost, and then we have to import these libraries. So let me run this and let me install cut boost and extreme gradient boosting and import them. It may take some time to install these two libraries. So until it installs, let's look at the hyperparameters. Now most of the models have hyperparameters that should be tuned. So okay, here just the XGBoost and CutBoost is successfully installed and it is imported. So let's look at the key hyperparameters to be tuned. For linear regression, we don't have specifically a hyperparameter to be tuned. For ridge, lasso, and elastic net regression, elastic net and also Hooper regression, we can have alpha, which is the regularization hyperparameter. And in the elastic nets, we have also another hyperparameter which is called L1 ratio, which makes a balance between the penalty of L1 and penalty of L2. So L1 ratio is in between 0 and 1. For example, by default it is, I think, okay, I'm not sure in general, but if L1 is 0.5, that means the balance of this ridge and lasso regression is equal, or L1 and L2 penalties are considered equal. And for the open regression, again we have alpha, which is a regularization parameter, and this epsilon is nothing but this is that of the cutoff point for utilizing Hooper regression, a squared loss or absolute loss. So if the error is greater than this epsilon, the Hooper regression will use the absolute loss. If the error is less than this epsilon, the Hooper regression will use that of the squared loss. And similarly, in the support vector regressor, as we have seen in the previous video, we have C, which is a regularization parameter, and actually this C is something like the inverse of alpha. And we have also epsilon, the kernel type, and also we have what we call that of the gamma. And for k nearest neighbors, we have number of neighbors, and for the others, we have also this number of these possible types of hyperparameters. For example, for a random forest regressor, it is a combination of decision trees. So we have a hyperparameter number of estimators. This number of estimators is nothing but number of decision trees. So if the number of estimators is 100, then the random forest regressor depends on 100 decision trees. And the same story for that of gradient boosting regressor, extra trees, bugging, ADA boost, extreme gradient boosting, and so on. And the cut boost, we have number of iterations and learning rate, and so on. So we have this sort of hyperparameters to be tuned for each type of regression model. So for tuning the hyperparameters of this regression, this and other models in general, we need to use the method which is called grid search CV. And again, we saw also this procedure in the previous videos. We need to call the method grid search CV, name of the model, the parameter grid, number of cross validation, and this is just for returning the train scores. And one thing that's most important is we need to add this one. If it is better to add this one in case if the model, because here the model is going to work on, let's say, 10 different folders or 5 different folders, but sometimes modeling on a specific fold may not be possible. Then in that case, this grid search may not work. Therefore, to see the actual error or to know what happens internally, it's better to add this option, error score, then we say in single or double quotes raise. Then this will automatically, if there is an error, it will automatically tell us what type of error or what type of error is being occurred or the cause of the error. Therefore, first we need to instantiate the grid search CV. After instantiating, we need to supply that's of the input features data and call the method fit. Then once fitting this grid search model, we can get the best optimal hyperparameters using the best params attribute, and we can get the corresponding best score, cross validation score, using that of this best score method. So this is just something to print out, this is nothing. So I have converted, instead of writing this code so many times for each model, I have just converted this into a certain function like this. So I just need to call here get optimal hyperparams, and then I have to provide the model, the parameter grid, the trained data, and also the test data. So this is just the ones that we saw in the previous videos, but this is converted into a certain function instead of typing these 4 lines of code so many times, because we are going to repeat for each model. So now I run this code. So let's start from that of ridge regression. For linear regression, we have no hyperparameter to be tuned. So for ridge regression, we have regularization parameter alpha. So if alpha is small, the regularization is weak. Then the model will act like that of the usual OLS regression with no penalty. And if the value of alpha is large, in that case, the regularization is going to be stronger. The regularization is to be stronger. So stronger regularization, then that shrinks the coefficients or the weights associated with the different covariates to 0. So first we have to instantiate our model of interest, ridge, and we have to define the parameter grid. Let the value of alpha be in a log space between -3 and 5, and let's select 50 values. Then here there are 50 possible values for this alpha hyperparameter. Then 50 models are going to be fitted. Of those 50 models, we are going to select, or the algorithm is going to select the one that performs best in terms of the R-square performance. Then if you run this code, you will get the best cross-validation score is 70%, and the actual train score is around 75%. And is the test score. So if you compare this best cross-validation R-square and the actual training R-square, 70 is smaller, the 75. So for example, here it seems there is still a slight overfitting problem, because the model trained on the full training set has a larger R-square value compared to the cross-validated R-square. So it seems there is a slight amount of overfitting, and the optimal value of alpha for that yields this 70.15 cross-validation R-square and 75% train R-square is 0.59. Of the different 50 values, this is the one that gives the maximum cross-validation R-square. And for lasso regression, again we can use the same procedure. Then it will yield, for example, the cross-validation 69.9%. So it is lower. So the ridge regression is better than the lasso regression, because here the cross-validation score is somewhat smaller. And the optimal value of the ridge parameter becomes 0.0517. Now for elasticnet, we have two hyperparameters. We have alpha. As usual, you can set a value in the log space between -5 and 4, and let's consider 50 values. And for L1 ratio, we can consider values between 0 and 1. But here I considered from 0.001 to 0.1, and let's select 10 values. So here we have 50 values, here we have 10 values. 50 times 10, 500. 500 models are going to be fitted by this research model. Of those 500 models, the one that provides the best R-square is going to be selected. So the best cross-validation score becomes 70.15, and the optimal alpha is 0.0016, the L1 ratio is 0.001. And for Hooper regression, again we have the regularization parameter alpha, and we have this epsilon, which determines when to use that squared error or absolute error. So for alpha, we can consider as usual, but for epsilon, let's say log space from 0 to 3, and selecting 10 values. Then here 100 models are going to be fitted. So the best is 70.14, and the optimal alpha is 0.10, and epsilon 4.64. Then for example, if the error is larger than 4.6, then the Hooper regression will use the absolute error. But if the error is less than this 4.6, the error that's going to be used in the Hooper regression is that of the absolute error. And the support vector regression, we have also C, which is a regularization parameter that balances the trade-off between maximizing the margin and minimizing the classification error. So here a small value of C means more regularization. In the case of alpha, a large value of alpha is here in the standard regression models. Large value of alpha is a larger regularization or larger penalty. But here in the support vector regressor, see, if it is large, it's less regularization, and if it is small, it means it is more regularization. And we have also another, the gamma, which is applicable only for radial basis kernel that controls the impact of or the influence of a single training example. So if gamma is small, that means the influence of a single training example is large. But if gamma is large, in that case the influence of a single training point will be small. So we can determine the kernel something like this. Kernel type, linear kernel, radial basis. C, a log space between 0 and 3 and 5 values. Gamma, again a linear space between 0.01 to 3, and let's select 5 values. So here we have 5 times 5, 25 times 2, 50. 50 models are going to be fitted, and it becomes 88.14. And the optimal value of C is around 178, and gamma 0.75. And the optimal kernel is radial basis kernel. And for k-nearest neighbor, let's focus on the number of neighbors in general. If the number of neighbors is small, that means it will be very sensitive to local fluctuations. But if it is large, the model will consider a larger neighborhood. So for k-nearest neighbors, again you can define number of neighbors, and then let's consider values from 1 up to 10. This here range 1 up to 11 lists values 1 up to 10. Let me add here list to see the values. Yeah, here we have 10 values, right? Therefore here 10 models are going to be considered with neighbor 1, 2, 3, and with a maximum of 10 neighbors. So here, for example, the best number of neighbors becomes 3. That gives the best cross-validation R-square 72.77. And for the second regressor, we can also make the same maximum depth of the tree, minimum sample splits, and also we have a criterion which is similar to that of the loss function, whether to use squared error or absolute error. We can optimize this one using the grid search CV, and it will provide the optimal values of this decision tree regressor. Similarly, for a random forest, we can do the same number of estimators, that is number of decision trees between 10 and 200. Let's select 10 values. Criterion, simply say squared error, so it will give again the optimal values and their performance measures. And for gradient boosting, number of estimators, and here we add, or we have another hyperparameter which is called learning rate. So we can optimize this one, and for extra trees the same. We can use number of estimators and criterion hyperparameters, and will provide these results. And for bugging the same, the procedure is almost the same. And for ADA boost, again we can use number of estimators and learning rates hyperparameters. For extreme gradient boosting, number of estimators, learning rate, maximum depth can be considered. For categorical boosting, we can consider learning rates only. So here in general, here what we have been doing is we have just finding the optimal hyperparameters of each model, which is very tedious and exhaustive. So the recommended way is, instead of tuning the hyperparameters of each of the candidate model separately, like the one that we did here, it is better to compare the models with their default hyperparameters and select the model that is promising and tune the hyperparameters of those promising models. That would be better. Otherwise, tuning the hyperparameters for each model like here is very exhaustive. Just starting from ridge regression, lasso, elastic nets, Hooper, support vector regressor, k-nearest neighbors, decision tree, random forest, gradient boosting, bagging regressor, ADA boost regressor, extreme gradient boosting regressor, categorical boosting regressor. So tuning each model and then comparing is not that much visible. So what is recommended is just instead of tuning each model and compare them, it is better to compare the models with their default hyperparameters. After comparing the models with their default hyperparameters, we can select the model that performs best and we can tune the hyperparameters of that best model. That is the easiest way of making comparison and tuning the hyperparameters of different models. So here we are going to consider the previous 15 models. So here I present all of them into a dictionary. Name of the model and the class of the model, linear regression, ridge, lasso, and so on. Therefore, this is a dictionary consisting of the name of the model and that's of the class of the models. So if I call it here, therefore here linear, the name, linear regression, ridge, lasso, and so on. Therefore, these are the instantiation of the models. For XGB, for example, the instantiation is something like this, right? It displays the parameters. Here, what you instantiated is just calling XGB a regressor, but it shows the parameters by default. And for cut boost regressor, the same. Cut boost regressor and that's of ADA boost regressor and so on. Therefore, this is just the creation of a dictionary, name of the models and their instantiation class. Then we have, let's say, how many models do we have? How many models do we have here? Number of models is nothing but length of the dictionary. We have 15 models. What is the type of each model? The one that we have specified here. Type of each model: linear, ridge, lasso, Hooper, and so on. So just the case here. We have specified these models. Names of these models are specified like this one. So it's just a dictionary. Here, it's better to create a dictionary consisting of all the model names together with their corresponding instantiation class. Then we are going to compare the models in terms of mean absolute error, mean squared error, and the R-squared performance. But the R-squared is the better way because it is a normalized version of the mean squared error. So I just wrote this code: evaluate model, give the actual outcome variable, the predicted outcome variable, then it will return mean absolute error, mean squared error, and the R-squared score. So it's just a definition to display these summary measures. Now here is also a function that is going to train the different models. So here I have to supply the regression models dictionary, which is this one. Name of the models and the models to be trained. And we have to supply the train and test data. Let's say this form. And here this is just a dictionary for storing the summary measures of the models: the train mean absolute error, train mean square error, train R-square error, and test mean absolute error, test mean square error, and test R-square score. So this is just to store the model scores, including that of the model name. Then for each model, it is going to train the model, get the prediction of the train and test, and evaluate the model and get here mean absolute error, mean square error, R square for both of the train and test data. And these scores will be stored here in the model scores. Then finally, this model scores is converted into a pandas data frame. And finally, this function will return the model score data frame. Therefore, just a simple function for training the different models and providing that of the summaries of the models, including mean absolute error, mean square error, and R square for both the training and testing sets. So let me run again this function. Now I run this function. Now I can call this function and give rig models dict, the one that we have specified here. We need to pass this one, and the rig models dict should pass through these train rig models, and we have to supply the train datasets and test datasets. Then this will train each and every model and provides the summaries of these values in a pandas data frame format. So let me run. Okay, it may take a little much time. Okay, that's good. Now it displays for linear the train mean absolute error, train mean square error, train R square, test mean absolute error, test mean square error, and test R square. But here we will look or concentrate on just the R square values, the train R square and test R square, because it is more interpretable. So we have to select the model, the one having a larger test R square. 91 here. GBR gradient boosting model has the largest test R square. Let's order this data frame using this test R square for just comparing the models. So here the one having a larger test R square is gradient boosting regressor. The second one is extreme gradient boosting. Third, categorical boosting regressor, right? So here the train R square for gradient boosting R square is gradient boosting regressor is 0.98, test R square 0.91, so it's good. And again extreme gradient boosting 0.99, 0.90. Now this seems to have a little bit an overfitting problem, because it explains almost all the data, all the training data, but the performance on the test set is somewhat low. And the same is true for that of categorical boosting regressor. The train R square is 0.99, so again it fits the data very well, but its performance for the test set is somewhat low. So this extreme gradient boosting and categorical boosting regressor seems to have some overfitting problems, but we can consider gradient boosting regressor, extreme gradient boosting regressor, and categorical boosting regressor, and we can tune the hyperparameters to obtain a model that is neither overfitting nor underfitting. And most importantly, for example, if you look at here, extra trace regressor and decision tree regressor, the train R square is 100%. Therefore, this extra trace regressor and decision tree regressor have overfitting problem or severe overfitting problem, because their performance in the test set is low, 85%, and here again around 85%. But their performance in the training is perfect or good or very high, or they have 100% accuracy or 100% explanation of the training data by the included input features, but their test performance is poor. Therefore, there is a severe overfitting problem with this extra trace regressor and decision tree regressor. So we do not select this model. So as a candidate model, we can consider gradient boosting regressor, extreme gradient boosting regressor, and categorical boosting regressor, and we can tune the hyperparameters, and finally we can compare these three models and select the one that performs best of these three models. So extra trace regressor and decision tree regressor are some overfitting problems, and we can consider the gradient boosting regressor as the best model. So for example, for the gradient boosting regressor now, because once we select it as best model or best candidate model, we can tune for this model instead of tuning each model separately. Because it is promising, we can tune using this code. So the best cross validation score will be around 85.58. The train R square becomes 0.9921 or 99.21%, and the test 91.6%. And the optimal hyperparameters for this gradient boosting model is learning rate 0.1 and number of estimators or number of decision trees 200. And if we are interested, you can also tune that of the gradient boosting regressor. What do you mean? Gradient boosting regressor, yeah. Okay, sorry, this I should say this, not RF, but gradient boosting regressor. And I have to say gradient boosting regressor. Gradient boosting regressor. And we can run again this one, but the result should be the same. Just here I named the value of the object as random forest. So this code is not okay, yeah. Once we obtain these optimal hyperparameters, with these optimal hyperparameters we can retrain the gradient boosting regressor learning rate 0.1 by specifying number of estimators 200, and we will get almost the same value. So the train R square 99.1, the test R square 91.6. So we can obtain the same train and test R square values by retraining the gradient boosting regressor, or we can get the best R square values from the grid search model, and we can also get the train and test R squares directly from the grid search model. And lastly and very importantly, we have to identify the relative contribution of the different input features. So we have to consider what we call feature importance, which measures how much each feature contributes in the prediction performance of the model or in reducing the model's prediction error. So higher values indicate that the feature is more important in predicting the outcome of interest. So for linear models like that of linear regression, lasso regression, ridge regression, elastic net regression, and Hooper regression, we can just look at the attributes coef. We can just look at the coefficients. Then a variable having a larger coefficient is having a larger contribution to the model, and the one having a smaller coefficient is contributing less. So the feature importance for linear models is just looking at the coefficients, but we have to keep in mind that for linear models we have to standardize or normalize the input features. Otherwise we can't directly take the coefficients as the indicators of the feature importance if the input covariates are not standardized or normalized. But once we normalize or standardize the input features, we can directly consider the coefficients or the weights associated with the different covariates to identify which variables are more important and which variables are less important. And the other for tree-based models, there is an attribute called feature importance. So we can call this feature importance attribute over the trained model for those tree-based models like decision tree regressor, random forest regressor, gradient boosting regressor, extra trees regressor, ADA boost regressor, extreme gradient boosting regressor, and categorical boosting regressor. These all have this feature importance attribute, therefore we can call this attribute to get the feature importance. So here, for example, we have selected the gradient boosting regressor as the best model for our comparison here, let's say. So let's see the feature importance of the model. Then here we have already trained the model, or let me train again. Yeah, here we trained the model GBReg, right? So GBReg, I have to call the method, no, I mean the attribute feature importance over it. So if I run, these are the feature importance of the different input features. But to look at to which this value, or to which variable, or to which input feature these values correspond, let's extract the feature names from the transformer. So the first one is chas1. This is the impact of chas, right? Second, crime. This one is for crime. So just for making just the comparison easier, let's convert these features names and feature importance scores into a data frame. For that, we can use these 3 lines of codes and convert into a pandas data frame. So it looks like this one, and it is sorted based on their importance or relative contribution. So for example, RM is number of rooms of the house, so it has about a 41% contribution. And you have LStats. LStats, what does it stand for? I forgot it. LStats. LStat, yeah, the percentage of low socioeconomic status of the population, right? Low socioeconomic status. So here, of the different covariates, number of rooms in the house and the socioeconomic status are the most important factors of the different 13 input features. Therefore, the relative contribution of number of rooms and LStat are the largest one, or these two models contribute much, or in general they contribute about 78% of the variation in the predictive signal, right? Therefore, overall of the total 13 input features, these two variables dominate the contribution, or dominate the prediction of the model. And the others, we have also some low importance features, like here RAD variable, this index variable, and tax, and even this here, this chas variable has the lowest contribution, right? The lowest contribution. So here the first one, smallest is index, okay, then RAD, ZN, and the chas variable R, the one having a low or lowest contribution are these variables. So whether the house is near to the Charles River or not, it doesn't have that much impact in making the prediction. But here, this shows only the importance of the variables, but it doesn't indicate the cause and effect relationship. So here, even if we say a number of rooms and socioeconomic status have or are the most important factors in the predictive performance of the model, it doesn't mean that these are the causes for making higher prices or for making lower prices. Therefore, here importance is different from cause and effect relationship. Cause and effect relation. Okay, so yeah. And the other, we have also some models without direct feature importance. So for linear models, we can extract the feature importance using the attribute COF, provided that the input features are normalized or standardized. For tree-based models, we can use this feature importance attributes. And there are also some models which we do not have, they do not have feature importance attributes, like that of support vector regressor, k-neighbors regressor, and bagging regressor. So for this, we are going to consider what we call permutation importance method. We have to import this permutation importance from scalar inspection, and then we just call permutation importance, need to provide the estimator of the model and that of the data, and number of repeats, the higher is the better, and random state for that of the initialization for ease of reproducibility. So from this we can extract this importance main from this permutation importance class. So for example, let's consider simply a support vector regressor, and then let's train the model. Now the model is trained by supplying this train in input features. Then we have to import this permutation importance from a scalar inspection, and then supply the estimator and the train and the input features. Here, let me change this first to train. So, okay, and was it? Found input variables in constant number of samples. Okay. Oh, sorry. Here I have to say train. So input features using that of the train set. Now here for consistency, it is also good to look at the feature importance based on the test sets and compare and contrast whether the input features contributing to the train set are also contributing to the test set. Okay, yeah, so we can compare these values, whether each values have actually the same contribution in the train and test sets. So here, based on the test set, for example, L stats, that's the socioeconomic status, and room are having the largest contribution. What about based on that of the train set? Let's say, let me run this again and go directly to here. Okay, yeah. Therefore, for both the training and testing sets, this L stats and RM, or socioeconomic status and number of rooms, have the largest or the greatest contribution. Therefore, here in using this permutation importance method, it is better to run for both the training and the of testing sets and compare and contrast to check whether the features that are contributing in the train sets or in the train predictive performance are also contributing for the test prediction performance. So in this permutation performance, it's computed by randomly shuffling each feature and measuring how much the model performance drops. So here each feature's importance is just the performance metrics, like that of the root mean square error. So since the metrics like root mean square error, mean absolute error, and the R-square score do not lie linearly, then the importance are not constrained to sum 1. So this sum of values are not necessarily 1. And even some of the variables may have even negative importance. So for example here, ZN, chance variable, crime are the input features having the lowest contributions or just almost no contribution, but even some of the variables could have negative contribution. So here, for example, let me run the permutation importance over the test set, and let me construct this data frame again. Now you see, even the feature importance, the test set for Zn becomes negative. Therefore, these feature importance are not necessarily sum to 1 for this permutation importance variable selection method or variable important variable identification method, because it is constructed by randomly shuffling each feature and measuring how the model performance drops or how the model performance, let's say, increases. So this is all about today's video. Thank you.